let's start from here on. I will tell you a little bit at first about the Hyperloop seminar, what we are doing, why we are doing this, and how this special session with the EHW came to be. So first of all, a very warm welcome to you to the special edition Hyperloop seminar with EHW. This time it's all about engineering for a successful demonstration for your pod runs next year in Zurich. In the name of all the Hyperloop seminar hosts, welcome. This is EHW and Swissloop, the founding members, and then we also have the Institute of Hyperloop Technology, where I'm from myself, with the University of Applied Science and the University of Oldenburg. We have Team Munich and also HART joined in right now with the Hyperloop development program as well. So this seminar started as a tool to disseminate Hyperloop knowledge and have some lectures and seminars where students can attend, learn about Hyperloop, and then also present their topics, thesis. But we also wanted to include industry experts. By now we have a lot of talks from industry experts as well that came from many different industries and having their view on Hyperloop, whether it is maintenance, legal, aerodynamics, levitation, many different topics. Yeah, some in the last years, I think last year at EHW, there were growing some thoughts during the competition in Edinburgh that we should have some lectures and seminars for distinct topics for teams to learn, gather the knowledge and improve their pods and research for the next year as well. So that's what we hope to do with this. And as a member of last year's jury, I can really speak for the whole jury that we welcome this talk today very, very much. And we hope that you make a lot of notes, take a lot of what is said today with you, and improve your designs and pods for next year. If you want to, you can rename yourself in the chat to include your team name as well, if you would like to. And then also in the chat, we are taking attendance with all the country flags we have in the seminar today. So let's start with the Hyperloop seminar. This is the goal of the seminar, basically talking to Hyperloop, talking about Hyperloop, bringing Hyperloop closer to the public, but also disseminate knowledge of experts and student thesis and everything like that. You can also put yourself into a student thesis here for Hyperloop and then contact one of the hosts, for example. And we are pretty happy to have new thesis and research about Hyperloop there. In the chat, there's the question if this meeting is recorded. Yes, it will be recorded, and we'll try to upload it afterwards. You can see that there's a schedule for the seminar. It's normally Wednesdays, 17 to 18 o'clock Central European time. Convert that to your time zone. There's also a calendar link that you can subscribe to that gives you all of the events directly into your calendar. And we'll also add the special sessions from EHW in there. So subscribe to this calendar link. It's also included in all of the LinkedIn announcements that are made. So you can find the link there. So no problem if you are not able to scan this QR code right now. So this week, next Wednesday, I hope you all will join. This is a very important topic, I guess, for thermal management systems of Hyperloop. We'll see a lot about the different options, but then also the manufacturing and simulation of a phase-changing cooling module for Hyperloop. And we've seen that last year at EHW, and I hope everybody who wants to take part in next year's EHW can see these talks next Wednesday, because very good talks that we've seen there. Then just introduction of the hosts, just real quick. Swissloop and EHW started it very early on. I've mentioned that they've put it into the curriculum as well. Very nice to see that Hyperloop has found the way into studies as well, with the teams from Swissloop and then also EHW, an organization who is a non-profit, is doing research on Hyperloop in an incubator. They are basically, they will be providing research and development, but also a test facility, and then later on probably branch into certification and regulation. We have the Institute of Hyperloop Technology, where we are also part of a few projects. We are mostly looking at cargo right now, but then also are building our own test infrastructure here at the university, where we'll have a vacuum chamber, and then also looking out further to a big, large-scale research infrastructure that will enable something like a 32-kilometer test track, continuous test track that allows for certification of Hyperloop at the end. We have two in Munich with a demonstrator that you've probably all seen recently that has been finalized in the summer. And you probably will see a little bit more about that soon. Then we have the European Test Center, the European Hyperloop Center in Groningen, in Windam specifically, that is built currently from hard Hyperloop, where you can really see that the tubes are laid down right now, and it's very interesting to have a switch integrated there as well, magnetic switch for the pods to see that first time here as well. That's what it will look like when it's finished. And then finally, I just want to tell you that you can ask questions here in the Q&A tool in Zoom directly. Please not ask anonymous questions if you want to. Then I would like to, after each presentation, call out your name. You can ask your question directly, but please put your name and your question in the Q&A tool. I'll call your name. You can ask your question. I think we'll have a little bit more of a discussion when we do it this way. And I don't need to read all of the anonymous questions that we have. You can also do that, but it would be more nice to have direct questions. Then you can vote on the questions. So if there's a lot of questions coming in, and I expect with so many participants here that we will have a lot of questions, please vote up and vote down. Vote up. I guess you can only vote up. Vote up the questions that you feel most relevant, so we can ask those first. And then just one last thing that I want to announce is we have a YouTube channel called the Hyperloop Seminar, and there's all the talks from the previous 3 or 4 years now that are on the site available. I know they're not very searchable, so we've created this, which is a database with all of the talks from industry experts and student theses about Hyperloop. You can search by keyword, you can go for the presenter, you can go for the company or the institution that has made the talk. There's the title of the talk, the direct YouTube link with a mark for the direct minutes of the YouTube video, and a short abstract that is, I think, 100 words long or something like that. So this will be in this link. I haven't posted this anywhere. We will post this probably Wednesday with the next announcement, but you will find that on LinkedIn as well. For now, this is the only place where you can get the database with all of the talks organized in this fashion. And now let's just jump right into this, to our engineering for successful demonstration from EHW today. And I think the first speaker will be Mario. So I'm happy for you to be able to share your screen and take over the microphone. So the floor is yours. Mario has been a part of EHW, I think, the last year, where he has been in the organization as well. But then also he has knowledge of developing systems for the Hyperloop prototype, as he has been responsible for a levitation system of the Delft Hyperloop pod. There we go. The floor is yours.
Thank you very much, Lucas. All right. Well, welcome everyone. Thank you for coming today. Today we decided to make this special session, especially for you. We've seen in the past years there's always complications with a lot of teams. It's understandable. There's a lot of complicated topics to treat in one prototype. And we have seen that especially teams that are starting new or have less people or time to put into the project have a lot of issues in the end to pass scrutineering, especially due to safety issues. So we would like to have this session for you to just get an understanding of how we think of safety and how we test our system, so that we can ensure that all the competition will go without any hazards or safety issues. So today we'll talk, first I'll do the first side. I'm going to be talking about mechanical and the electromagnet design. And then later, Alejandro, the other lead from the department, will talk about mainly electrical and software. So let's start with the mechanical design. There's a lot of several parts in the mechanical side of the prototype. We can start from the chassis. We'll focus this session especially on a complete system, since it's a bit easier to provide an overview in this sense, but please feel free to apply this to your specific situation. You're only building specific subsystems. So the chassis is mainly in charge of providing the structural integrity to the pod. it has to host all the different subsystems there is within and just keep them in place. It also determines greatly the shape that your vehicle can have. And then on top of this, the chassis can also be at the same time the structure that provides the aerodynamic characteristics of the vehicle. In addition, in the future, it would hold also the passengers for the vehicle. So I wanted to include a few inspirations that a lot of teams take from the industry, already existing industry. For example, an aircraft frame. This is really good, especially in aircraft that we have a pressure difference between the inside and the outside. So this circular shape can provide a lot of benefits, reduced amount of weight in comparison to other shapes. So this could be specifically beneficial for passenger transport, where we would need to maintain one atmosphere of pressure inside the fuselage. In addition, we could also consider, well, how a car would work. So the teams this year are not bringing passengers, so we don't really necessarily need right now an aircraft frame. So I think we'd go, for example, for an aluminum structure like it's done in a lot of cars. Similarly, in order to just reduce weight, you could go for a composite frame, normally also done with mixes of steel parts, aluminum parts, and composites, normal carbon fiber. Here I have some examples of what teams have brought in past editions. On top you have Hyped chassis. On the bottom left you have Swiss Loop's last year chassis. And you can see that this one has integrated, for example, the holding all the components in place and the aeroshell itself to provide the aerodynamics. But for example, in Delft's Hyperloop case, it's mainly made of aluminum profiles, and then on top of it there goes the aeroshell, which is attached to it. Must be said that if this is done, the aeroshell part would also have to be attached mechanically properly. It can't be done with just simply keeping it in place with a magnet, for example. Taking into account. And a few design considerations. You can find all the rules in the R&R. It's in our webpage. Also send it through email. But I put one of the rules here, for example, that you must keep a higher safety factor higher than 2. So this you have to apply for a lot of different load cases that you have. So for example, just the weight of the individual subsystems, where they're placed, how does the weight and the placement influence your chassis, how much is going to deflect, if it might buckle, for example, those kind of things. Your design will also mainly be influenced by the weight. The materials you choose, as I said, carbon fiber, aluminum. Something that we have find very, very important in the past editions for a lot of teams is accessibility of the subsystems. So that is something that, for example, if you have a composite structure that covers entirely the subsystem, it might be very hard to reach into specific areas. And it's something maybe good to take into account in the first stages, since it might save you a lot of time during testing, and it will make it easier in general. I put some examples here of profiles you can use, for example, that are already used in industry and might make it easier for you, that you don't have to design it. They're already rated, and you know how many loads they can sustain. So feel free to get some inspiration from it. And then something you also have to take into account, I just put it so that you can also learn from past year's mistakes. There's a rule that states that the MIDs, so this respect with high voltage batteries, that they must be accessible without the use of any mechanical tools or removing any other parts. So as an example, last year, Delft Hyperloop's aeroshell, you could not access the MIDs with the aeroshell on. and therefore the jury required them to make holes so that you could access them. Also, just for you to take it into account that you don't get to the competition, and surprisingly, you have to make a quick change in design. If it's an aluminum part, it might be a bit easier to cut, but for example, here, if it's a carbon part, you will need the special tools, the special environments to do all of this. So just for you to take it into account. And I included a few tests that you could do. The philosophy we would like to approach with tests, we don't want to impose specific tests on you, but we would like you to think critically about what tests you would like to do. So for example, you will perform a FEM analysis on your chassis structure just to see if it will hold, if it satisfies that safety factor of 2. But to validate that your FEM analysis have been performed correctly, or that your chassis actually follows that design, you want to make tests. So one example is, for example, make a bend test. So put a load on the chassis and see how much it deflects. And if you compare that to the results of your FEM, you can estimate if the FEM is similar or if it will perform in the same way that you intended to. Other tests that could be done, for example, is in case you have a levitation system, what would happen if it would shut down and your pod would fall down, if the system can withstand those loads, or vibration tests because of interfaces with the track or propulsion that can cause vibrations. These are just some examples of tests that you can. Yeah, this was it for the chassis. I don't know if there's any questions. Otherwise,
I haven't seen any questions yet in the Q&A tool.
All right.
Feel free to post anything in the Q&A tool that you have on your mind.
Yeah, I think we can continue, and then if there's more, we'll stop.
Oh, there's two. There's two questions. Sorry, it was on the wrong tab for a second. Okay, that is definitely not a question.
No.
You also need to consider accessibility for low voltage systems.
All right. I would recommend that you consider it especially for maintenance and being able to access all the wires that you connect. I believe there's no MID requirement for the low voltage system. So you don't have to consider it in that sense, but it is always good for you to be able to access it. I don't know if, do you have a better way of answering the question, Lucas?
I don't know. Eshwar, is this what you wanted to hear? Sorry, I wanted you to ask the question. I forgot.
Oh, sorry, I was waiting for the prompt. Thank you for the answer. So I'm a new member actually in mu0 Hyperloop, and as far as I understand, we have, I think, a 44 volt battery this time, which is low voltage still. And for this, is it okay if we don't have any holes in the shell? Of course, like we will channel all the wires and everything, but is it okay if we don't have any holes in the shell, just to know ahead of time for the design?
Maybe Alejandro, you can ask more and you answer that question.
Really? Yeah, no problem. Can you hear me correctly?
Yeah.
Okay, nice. So good evening, everyone. I'm Alejandro. I'm Mario's colleague. I'm the technical lead. So as for the accessibility for low voltage systems, I'd say that if your accessibility problem is the aeroshell itself, then there is no problem, because you do not require any MID or external disconnection button for the low voltage systems. You would want to control them from the control station. And you also have to take into account that, being realistic, you will only use the aeroshell at the hour age on the demonstration, because when you're doing testing on your facility, you're not going to wear the aeroshell. Probably you will have used the system without the just with the chassis. So if you're talking about that, when you just have the chassis, please make sure that you can access from there the low voltage systems, because you will need to put wires, you will need to change things. So yes, that's the deal with that.
Okay. Okay. Thank you. So if the only barrier to accessibility is the aero shell, it's not a problem for low voltage systems at the EHW.
Not for low voltage systems,
Okay.
exactly.
Thank you.
You're welcome.
Then we have another question in the chat from Ritwik. You're asking how to demonstrate the chassis. Maybe you can elaborate on that.
Hi, can you hear me?
Yes.
Yes.
Yeah, thanks for the opportunity. It's just wanted to ask about, like basically in the mechanical subsystem award rules, and there's also the other subsystem like guidance and stuff. It's you need a demonstration, right? So do we have to move the chassis to show it works, or do we have to just bring our fully built chassis with like vibrations and all these other tests results to show that it's demonstrated? So what classifies as a demonstration is my question for just the chassis, suspension, and let's say a maglev, for example. I don't know. I mean, let's say mine without the maglev, just chassis, suspension, aeroshell. And this is a mechanical suspension I'm talking about, not a with like wheels or something like that, or race bike dampers. Thank you.
Okay, thank you for your question. It's a bit specific. We haven't really looked at all the ITDs and all the specific demonstrations that team intend to bring. This is the first time we are just doing this subsystem demonstration, so it's a bit unclear of how that will work still. But I would say normally also when teams build the mechanical subsystem, they bring something else. So normally the mechanical subsystem itself, it's demonstrated by, for example, doing guiding, doing propulsion, just so that it can hold all of those components. But in the end, what you want to demonstrate also depends on you. And the jury, there is a score for demonstration. So in that sense, you have to think also of what would be more beneficial for you if bringing specific machines, specific tests set up that allow you to vibrate or put loads. In the end, depends a little bit on you. But as we said, also after the ITD, after we hand in the ITDs, we'll have a review session with you, and we can maybe specify a bit more the direction you want to go.
Okay, so I just wanted to get that piece of information that you'll have the review session so that we can tailor the direction a bit better. So I think that answers that bit. But yeah, it's quite vague, so it's a bit confusing for us. But hopefully we can email some more questions and we can get that out of the way. Thank you.
All right.
I feel like this is a very good question to the EHW to take into consideration how to do the testing for example, things such as a chassis. We've seen in last years, for example, what we in the jury quite much liked as well for the chassis or just the frame. Analysis on vibration, load testing parts or components of your chassis. So if you're manufacturing carbon fiber tubes or something that you manufacture your chassis with, if you test them before in a safe environment where you can probably break them or something under load, it would be nice to see that they hold the loads you expected. The engineering is nicely done on that. So some of those might be quite nice. And vibration testing as well. Where's your main frequencies that you want to avoid or something like that? Maybe you introduce dampers for that. So that's the engineering process probably is behind something like a chassis is probably very valuable to see that there. Then there was a question from Nick in the Q&A that is dealing with a completely different topic. I think I'll answer that later on. And then there is something that was put in the chat by Pranava. Maybe you can ask your question. Or Pranav? I don't know. Yeah, there you go. Yes, can you hear you?
Hello, am I audible?
Yes, yeah.
So as per the DM 4.2.3 rule in the RNR, it's stated, I've mentioned in the chat box as well, that any pneumatic or pressurized fluid circuit must be drawn with accompanying specifications, and all the vessels and enclosures must be marked with a certification nameplate with all the certified maximum allowable pressure ratings being provided. So all these ratings that are being talked about and the circuit that is being asked to drawn, is it expected for all these things to be specified on the physical device that is on the demonstrator, or is it being talked about to mention these details in the documentation that we submit, the FDD?
Right. Thank you for your question. I think it depends a little bit on the component itself. So, for example, if you have a tank that will store air pressure, it is very recommended you have it on you have the certification on the tank itself, just so it's easy to see, visible. But for example, if you have a tube that connects two pressure sides, I don't think you necessarily have to have a little etiquette saying the part name and all the specifications. So so I would say mainly the most critical parts.
Right. All right. Got it. Thank you.
And we'll go now into pneumatics as well. So if you have more questions, we can ask or answer.
Okay, Mario, then I guess go on.
Yeah. Okay. Let's talk a little bit about the track first. So the track has to do several functions. First, transfer all the loads from the pod safely into the ground, distribute them, provide a smooth and level surface for the movement of pods so that it's not vibrating all over the place. It could potentially provide a low pressure environment, so vacuum tube, for example. And also, it has to interface with levitation and the propulsion system. So the design of the track, the configuration mainly will depend on your levitation and propulsion subsystems, and also a lot on the length that you want to build your track. We wanted to put some examples of custom tracks that teams have built past years. On the left, you have a Delft Hyperloop track. It's a hanging track, so the pod is placed below the track. On the right, you have UPV's track to build a pressurized vessel last year. Then we have Swissloop track on the left, and on the right, the I-beam that is used in all the editions of the EHW. Here you can see me as Euro spot. So to design the track, there's a lot of things to take into account. I put some here, but you can better get all the rules and regulations from the R&R. We don't have time to go over all of them. But a lot of effort has to be put into integration with propulsion and levitation, especially the most critical loads that we have seen are impact, especially if you are levitating and you drop. There's large loads on the track there, so you should be able to withstand that, as well as if there's track misalignments and your vehicle is already touching the track and it hits a bump, that also creates a lot of loads. A lot of, for example, other safety configurations that you must include also are defining safety areas. So if there's any emergency, apart from the procedures of how to proceed from there, where should the people go and where everything can be fine. And some recommended tests to the track, either the individual components themselves. Most of them are in general off-the-shelf components, or available, public available beams and standard sizes. So those don't generally have to be tested individually, but it's good to check that the vehicle fits on the track, obviously, as well as do impact tests on the vehicle or perhaps vacuum tests, for example, in the case of UPV. This from the track side, not too much information, but you can take more a look in the R&R.
Okay, then first of all, I might ask you the question, will the slides be emailed to the teams?
Yeah.
To be able to look through the sources and so on. Okay, that's perfect. Then there's a second question from Ashwa. Maybe you want to ask your question yourself.
Hi, thank you. Yeah, it was regarding the testing for the pod itself. So you gave a few examples, and I was just wondering also what sort of superimposition of load cases should we consider, and then do we still need to dimension with safety factor of 2 with the worst case superimposed load that we can think of, or is it just each of the simple load cases and then safety factor of 2 um, for each of it? Yeah.
Thank you for your question. I'd say is the superimposed load cases. You don't have to impose all of them if they cannot happen simultaneously. So, for example, if you have an impact on the top of your track, you cannot have at the same time an impact on the bottom with the 4 wheels. So you wouldn't have to superimpose those 2 cases. But you do have to take into account the worst case scenario, and that might include several loads together.
Okay, thank you.
Okay, then there's one more question. Maybe I can do this quickly regarding the ITD. If the team has to can submit an ITD for multiple subsystem awards, like 3 awards here, as you see in the chat in the Q&A to Mario. Oh, sorry. Yeah, is it one document? Is it 3 separate documents?
Yeah, it's
the
just
limit.
one document altogether.
And they can compete for several subsystem awards.
Yeah, exactly. A maximum of 3. Yeah, and otherwise a complete system.
Yeah, and they will have to complete 3 TSDs and 3 FSDs, or will they need to hand in separate ones?
Also like the ITD all together in one document. But we will post guidelines for those documents later on the year, so you can take a look.
Okay, perfect. I guess that's that with the questions for this part.
Yeah. Okay, let's continue. Let's get into emergency braking. So the main function of the emergency brakes are to, well, make the vehicle stop at any point in time during demonstration. Well, this subsystem will mainly be sized either depending on the required deceleration that your team wants, or the braking distance at the maximum speed that your team wants. This is a subsystem that is very important in the sense that this subsystem has to work when everything else on the vehicle might go wrong. So you really have to take safety into account to design the subsystem. And in addition, the integration that it has with both electrical and the software subsystems. We'll start with a few design safety considerations that you have to take into account. So for example, what would happen if there's a misalignment on the track and you start braking and your braking pads go over that misalignment? Your vehicle should be able to withstand that. So it's something quite important to take into account. Emergency brake distance, since you will have to leave a margin at the end. We'll get into that later. Materials used, both for weight, also for not damaging the infrastructure or the track. And yeah, like I said, other integrations with subsystems. Some important things that are included in emergency braking is that your system, that the system should be able to brake if the control signal is not sent. So basically, how these systems are normally designed, there's a control signal that is continuously being sent to a PCB or a device that is controlling the brakes. And whenever that signal is cut, then the brakes will automatically deploy. This is done especially so that if there's a power loss, the brake will deploy and that there's no chance that that the signal to brake is not sent. So basically the signal to not brake is continuously sent, and when something goes wrong, that signal is not being sent anymore. Regarding the braking distance, you must leave a braking distance of, you must leave a distance at the end of the track of double the braking distance of maximum speed. So this means you leave quite some space at the end. So a lot of teams find very important to break in a really small amount of, a really small distance, so that maximizes the amount of space you have to perform your pot run. Something to take into account. And something else important is that your forces that you apply must be done in a symmetrical manner. This has a lot of implications. For example, if you decide to, if you think you could break on only just one side of the pot, you have to think that then there would be a moment and your pot will tend to yaw, and that's, well, it's not a symmetrical breaking, so this wouldn't be allowed. The only way that the breaking shouldn't be symmetrical is in the direction of travel. That's why we want to decelerate the vehicle. So some ways to break, for example, on the I-beam are well, applying forces in the directions that I show here. This image. Something also very important is, well, braking can be done with pneumatic friction or electromagnetic, but if it's done through electromagnetic and energy is being restored, you must test how much energy is being restored, handle it accordingly. Sometimes the batteries, for example, cannot take back that energy the proper manner, so it has to all be converted in some way. So that has to be thoroughly tested as well. So let's go into a few examples of braking systems that are used. Mainly you can divide them in two. The references are wrong here. Friction braking, which is applying a force directly through contact to the track, or electromagnetic braking, which is done mainly through, well, creating normally eddy currents on the track. Could also be creating an a field opposite to the one present on the track to slow down. So some ways that the braking, the deployment of the brakes can be done are direct or indirect. So indirect, direct refers to having a pneumatic system that the gas that is trapped, once that pressure is high, that the system is deployed. And the indirect refers that when there is no pressure, then the system is deployed. So basically they're the opposite to each other. And in both sides, we can find either pneumatic, hydraulic, or electric. I have an example for a pneumatic system, is the ones that we find the most in the EHW. So we can just go through this. There's a number of valves throughout. Sorry, let me start again. So there's this is just an example. You can, for example, base it off. I included it because it includes a lot of valves and sensors that we have seen that, well, this is safe in a way that it allows for, if there's mistakes, that it can be fixed in a safe manner in that way. So for example, we have a bleed valve at the beginning, which is a valve that if the pressure, if you set the valve to, for example, 200 bars and you accidentally overfill your tank to 250, this valve will make sure that the excess pressure will be released. And the release valve allows you to basically just empty the tank if you don't want to empty through the normal path it takes. Then we have a filling nipple, which is just to fill the tank itself. Pressure sensor to monitor. And then here we have a solenoid valve, which is a part that interfaces with the electrical subsystem. Basically, this valve is responsible to open or close the passing of air through the system so that braking can take place. And then at the end, there's another solenoid valve that will allow you to vent the system. So once the air is taken out of the system, the brakes will deploy. Something that I added here at the end is a ball valve, something to take into account. So for example, this is used a lot of times during testing when placing the pod on the track. It can be used to retract the brakes, and once the brakes are retracted, close that path, that exit path, so that it's basically a safety measure so that the brakes cannot deploy when people are in front, if the pod is being placed in the track. It has a double side. It is a safety advantage for people so that they cannot get damaged, but it can be a safety issue for your vehicle, since if this valve is kept close and the pod is allowed to perform a run, the system will not be able to brake. So if you do include this in your design, please take it into account in your procedures as well, that you have to check this valve is open once you do a demonstration. You could also do a pneumatic system. That was an example for a low pressure system, but you could do a high pressure system. This would just be divided right before the solenoid valve, and a pressure regulator would be added, as well as an extra air relief valve. For hydraulics, I don't have a lot of knowledge on that, so I would recommend you to do research of your own. The systems are quite similar to the pneumatics, but the springs are normally placed earlier in the diagram, so that one spring can activate all the calipers. And some example of testing that can be done are testing different pressures on the system. On the right, I include a source of how you can progressively test different pressures. You could test on a flywheel first your system as well, so that you ensure that you can take all the energy from the system back. And in case you're using a pneumatic system, it could be also a good option to do vibration tests to check that under the vibrations the tube will not disconnect from each other, for example. So that was it for the emergency brake side. Do we have any questions?
I don't see any questions yet. Maybe we'll give everyone half a minute to maybe ask some questions if they're still typing. In that time, I can still answer Nick's question. Maybe I hope you didn't are not bad with me if I answer it right away, and maybe if I should elaborate on one point more, I can do that there. What's going on with China and the T-flight system? Oh, sorry. Do you want to ask yourself?
Yeah. I've been in this Hyperloop business before it was called Hyperloop.
ET3, yeah.
So ET3, and I met with Musk, 3 weeks before he released his paper, and so I've seen this whole thing evolve. And the whole time, if you look back at the history of it, the Chinese have been there the whole time, and they invited Daryl Oster in the year 2003 over there, and they just have been developing high temperature superconductors, maglev systems. And just recently I was like, oh, so let's go see what's going up with T-Flight. And they do have a LinkedIn page, and I was surprised to see the amount of progress that they've made. And they are, they have a full-on testing facility down there. It's very similar and maybe even bigger than what's going on in Europe. And they have vehicles going very fast, and they're using high temperature superconductors. So if the goal is to have a global system, shouldn't the Chinese be involved? I mean, what's going on with them?
Maybe a quick answer to that, and then I can elaborate if you want to. I've seen that system as well. That's based on the figure 8 call configuration. Everybody is familiar with cavitation systems, based on the L0 maglev of the Shinkansen maglev from Japan. I think the problem with this system is switching, which should occur in a Hyperloop system as well. If you want to build a network, for example, in Europe, you want to have switches, but you can do high-speed switching without any moving parts. If you can do that, then you can build up a Hyperloop system, Hyperloop network, And I think you can't do that with a high temperature superconductive figure-8 coil system. If anybody proves me different, please do so. But I think the only way you can do it probably would be up and down, and at least not left to right, which is a different thing in itself because everybody is putting Hyperloop tubes next to each other. I think the optimal solution will be to put them on top of each other. That way you can simultaneously go out and in to a city that's left or right in a high-speed network. Otherwise, you would need to go around and then cross again, like for example with a highway where you have that. And then there is standardization going on for Hyperloop, but mainly just in Europe for example, NJTC20 in Sen. So that's the place where standardization is going on, but China is not. There's no Chinese manufacturers or Chinese identities yet included in that. And
I had a question, but that's a great answer.
Within a continent.
Yeah, the Chinese really don't want to give people.
Within a continent, it should be fine. Yeah, but it doesn't need to have one system for the whole world.
Yeah, they don't really want to give individuals a choice of where they want to go. They just get it and go. So I just have a question about the development in Europe. I see different companies that have raised quite a bit of money and are doing awesome things. Very, very happy about to see the progress. But how does the heart system and like the transpod system, like one has a fan in the front and I see all these different Hyperloop companies. Now they say they're working together. What is the vision here? I mean, are they all going to eventually become one company? Like what is the end game here?
I think in Europe there's a lot more synergies going on right now. Let's talk about that maybe after the next few sessions here from the EHW or at the end of the seminar. We can go more into detail about that. But yeah, there's a lot of cooperation going on within Europe for all the Hyperloop promoters to work together with the Hyperloop Alliance they've built, with the Hyperloop development program that Celeros and HART, Nivomo are part of. So there's a lot of unified approaches within Europe and convergence within Europe that is starting to happen, which is good because it's one continent and we need one system for one continent. If in North America we have a different system compared to Europe, should be fine. Nobody wants to cross an ocean yet with Hyperloop. Nobody's thinking about swimming tubes that long. So that won't be a problem right now, probably more towards the future. But yeah, I would see one continent, one system, that should be fine. Maybe you can go on and I'll take your question the next time we have a bigger spot available. And then we'll go to Arturo right now. Maybe you want to ask your question. Thank you, Nick.
Hi. Yes. Pneumatic actuators to put the force on the truck. Here we're having a system that's fail-safe, that it cannot fail. Last year, if I remember well, in the rules, that it was like something that it should be one fault tolerant. If we need to have a fail-safe system, is it compulsory to have like springs on the actuator so that there is force at any time if with no air or no power? Or could there be a solution in which you could use double acting pneumatic actuators that always need air to make the force?
Thank you for your question. You basically have to ensure that your vehicle will come to a stop. Almost happens what happens. So, in this case, it does mean that you have to be continuously applying a force unless the system is told to not. That's why I said in general, indirect systems are used. Yeah, they're just more safe in that sense. And the redundancy as well refers to, so for example, I put an example with 4 braking calipers. In that sense, it's one fellow redundant, so that if one of the brake pads doesn't work, the vehicle will still be able to come to a safe stop. I don't know if that answers your question.
Yeah. Okay, thank you.
Okay, and then there's another question from Kevin. Maybe you want to ask your question as well.
Yeah, thanks a lot for hosting this. In the rules, it just talks about there being two types of systems. So you have like team-made pneumatic systems, and then you have commercial ones. And I just wanted to understand the difference. So say I buy a bunch of like pneumatic parts from a company like Swedgelock, and then I assemble those parts together myself and I tighten all the connections. Would that count as team-made, or would that count as commercial?
I'm not very sure on how it's strictly explained in the R&R, but I would say you don't have to test the individual parts themselves, so you don't need to see if the tube individually withstands the pressure that it says so, but you do have to test the assembly itself, because the company provides you with the parts, but not the assembly itself.
Right. So I would get the assembly, and then the assembly would have to meet the safety factor of 2. And then if it does that, then we should be good.
What do you think of that, Lucas?
Could you repeat that? Sorry.
Yeah, he was asking me. I guess what we've had the last years was, well, if you have pressure tanks, for example, that are designed to a certain to withhold a certain pressure, you should only operate them to this pressure. I think you don't have to test them if they're regulated to 500 bars, and they are normally then times 1.6 or something. There's a safety factor on that. You can operate them until the pressure that they are certified to and they are used to in normal operations. That should be fine. But you should show that your whole system also works. So all the connections you've made are fine and so on and so forth. So that is something you should test. But I think you don't need to test your your components itself to the limits that the manufacturer specified, like the limits above normal operation.
Awesome. Thank you very much. That makes sense. Thanks.
I think that helps. Okay. There is one more question from Eshra. Maybe you want to ask your question.
Yeah, hi, thanks again. So I was just wondering, once you design a brake system, perform all the calculations, at the end, if the force turns out to be less, then can we just start engaging the brakes earlier? For example, we have like a 50-meter track or something like this, and I think from the slide it said we should have the pod's length remaining at the end as the safety factor. So perhaps can we just let's say we had planned to engage it, I don't know, at like 45 meters, but then we see that the force is less, then can we just start engaging it at 35 meters remaining so that we have the safety distances? That okay, or is there some force that needs to be met as a ratio to the weight of the pod or something like that?
Yeah, this would most likely happen with consultation with the jury, but I can tell you that for sure you will need to leave that double distance of braking, like once you start braking.
So there's no set force, there's no like ratio of brake force to mass of the pod or something like this. It's just that whenever you want to start braking, you start braking, but at the end of the track you must have at least one pod length, right?
Yeah.
Okay. So
your braking depends on your system characteristics as well, what speed you want to reach and your mass.
Okay. So like if it all does not work out, you can just start engaging the brake earlier and then keep a safe system still.
Yeah.
Okay, thank you.
Yeah, I think some evidence-based data is very nice for the jury here as well. So if you have a 200-meter track at home, if you have a 50-meter track that you show at EHW, for example, and you propel yourself to the speed you know at home, brake, you show the jury that this is, and the scrutineers that this is the braking distance that you have with a full braking system. You can use that as your distance, and then you can also probably do a test with half of your braking system, or failures that you would expect, for example, from your 4 calipers, you have 2 not engaged. Also, like, remember, loads need to be distributed well there if you do that. But if you can show that too, where your minimum braking distance would be in case of any failure that you anticipate, that is very good. That is very nice to see and to have.
Thank you.
Right.
Okay, I think that's it.
Yeah.
I think we could go on again.
Yeah, let's continue. Let's speed up a little bit.
Yeah, how much do we still have left? How many?
We have a little bit of safety wheels and then the electromagnet side. So
okay,
let's we can just speed up and do question round at the end.
Yes. Okay.
So safety wheels. The safety wheels mainly have to limit the movement of the pot in the track, so that no parts not intentionally, no parts that are not intended to touch the track to touch it, and also just lower the loads that the vehicle will experience due to its interface with the track. So the safety wheel design will be influenced a lot by levitation, propulsion, and also the speed that you will attain. So some considerations that you might take into account when designing your safety wheels are, for example, the maximum accelerations that your electrical components can handle. I know a lot of teams also use like 10 Gs as a maximum. You have to look at your specific electronics. The loads that the wheels themselves can handle, if you have bought them, what they're rated or what you have designed them for. Balancing of wheels so that they spin correctly at around an axis. How much they would compress in case they would fall from a levitation system, for example, or during a normal run. Might also be interesting to know all the static compression. The material of it is also very important so that it shouldn't damage the track, especially if you're using the EHW infrastructure. There's rules on that. Want to refer to the R&R. And then some possible tests that you could do with them. Impact tests. So this would be together with the chassis. Some speed tests, for example, so that see if the wheels can handle the loads there, or what would happen if the vehicle would ride into a bump in the track and misalignment there, if they would be able to handle it. I put here some examples of wheels that teams bring sometimes. Like you have roller wheels. Well, these are used in carts, for example. I haven't seen them in the competition too much. And then on the right, well, some teams design their own brackets and just have their custom wheels in this sense. So here you have some inspiration. So let's get now into the electromagnet design for scale vehicles. We'll start with the levitation system and then we'll go into propulsion. So the levitation system has to mainly keep the vehicle from touching the track as much as possible. Also keep it at a stable air gap so that the motor can operate optimally and damp all the internal and external disturbances. So the effects that the drag has on your vehicle, the motor as well. Yeah. And your design will depend mainly on the weight of your vehicle and a lot as well in the motor drives that you're that you can have or use. So commonly in the past editions, the main systems that we have seen are EMS, so electromagnet suspension, HEMS, which is a similar version but uses magnets as well, and electrodynamic suspension. The first two are systems that need a control, an active control in them. They're unstable or neutrally stable, so the air gap has to be controlled by the current that is run through the coils. You can see on the bottom of the slides the working principles. You have some papers also there that you can check out. And the electrodynamic suspension is referred to normally, well, for example, used in an aluminum track where your vehicle contains a magnet, for example, and by going fast throughout that aluminum track, a counteracting magnetic field will be created on the aluminum structure, which will basically make your vehicle levitate. So in this sense, it's passively stable in the sense that if you get further away from the track, the forces will decrease and you will reduce your air gap, and The opposite also applies. If you get closer, your forces will increase and your air gap will also increase. The choice depends on you and what you want to also accomplish. Some other options that haven't been really seen in previous editions, but are also out there you could potentially use. You could look at the SC maglev. Lucas talked about it before. They use figure 8 coils to achieve stability. There is induct track as well, which is used in a few projects as well. We have rotating permanent magnets. You can watch a very cool video by Veritasium about them. Be aware that they will make your track heat up to the point where you can boil water. So watch out. And then you could make use of the Meissner effect with superconductors and magnetic track, for example. I included here at the bottom a reference to the Hyperloop seminar. There's a lecture specifically talking about levitation systems. I looked through it and it has a lot of information about them, so I really recommend it. And then specifically different parameters that you have to take into account characteristics of your system when designing it. So if you go for a HEMS or a EMS system, what material your core is going to be made of, what geometry does it guide the flux lines in the correct way, will the material get saturated. You have to choose your coils as well, so how many windings you have will determine the force that you can provide or the force reduction you can provide for your magnets. Choice of wire diameter, material, insulation, for safety mainly. There's a special interface with the propulsion subsystem, since they will also produce forces that will interface with the levitation. So we'll go a little bit more later on this, but it's something very important to take into account, as well as it interface with the safety wheels that you have. So if you impact, for example, and your safety wheels compress too much, it might be that the magnet gets so close to the track that you are not able to lift off again with your electromagnets, for example. And something else that is also taken into account by a lot of teams are eddy currents. So the full scale potential of your solution, how much drag it is going to cause, for example, or increase in temperature on your system. And something that also must be included in this design is the control side of it. If you go for an unstable or neutrally stable system, generally a lot of a good way and easy way to do it is by using a PID gain. You could go for other options, but is the easier way in that sense. And then the propulsion side, the motor is in charge of transmitting power to be able to move the vehicle forward. A lot of things also change, affect the design of this. So the pod weight, what acceleration speed you want to achieve, and as well for levitation, the motor drives that you use. We have seen in the past in the EHW mainly these systems. Linear induction motor, linear synchronous motor, and linear reluctance motor. They're basically adaptations of rotating motors that you can see in, for example, cars to a linear way. So you can find the working principles of them on the links I provide below. Some of them have more advantages than the other. So some will allow your vehicle to be lighter, while your track that has to do work, has to provide a current that does a magnetic field. The others work in the other way, so your track may be passive. And all the complex elements are your pod. It depends on your vision, also of what a full-scale vehicle should look like. We encourage you to take a look at this and maybe consider other options as well. For the propulsion side, apart from coils, magnets, and force, like it was for levitation, there's a bigger interface with the track. Since these motors have to work perfectly with the track. For example, the linear induction motor could work on an aluminum surface, so the track doesn't have to be powered or doesn't have a specific geometry that you would have to control. But for the linear synchronous motor and linear reluctance motor, there is a switching that is done, which depends on where the components on the track are placed. So this means that a lot of teams have to implement localization systems to be able to perform a run. So this localization system will tell you, so for example here, where the tooth of your mover is, or where the north and south pole in the track is, so that you can, in that sense, choose the orientation of your magnetic field in your motor. As I said, also here, you need a control architecture to be able to face these currents that you're sending with your track. And again, an interface with levitation. It's important to take safety into account in these two subsystems. I'll treat them together since there's a lot of common things between them. One other thing is the magnetic field around them. So this is especially important for people with pacemakers around, since they are very susceptible with this, but it's also very important for preventing tools from to fly towards your magnets, for example. So there's a cover that you must place around your magnets whenever they're not being used. So once you arrive to the EHW location, you will have to have your magnets covered the whole time until inspection has happened. And whenever your magnets are not being used, they have to be covered as well. So in that sense, you have two options to build a magnet cover if you do have permanent magnets on your vehicle. It can be just very big enough so that at that distance the magnetic field is less than the required, or you can make it smaller and build it of a ferromagnetic material so that it guides the flag lines in such a way that they don't exit that enclosure of that cover that you have. And in addition, I would like to have special focus on the coils, since they carry high power, they have high voltage, high currents. They're very dangerous parts of the systems. So what we have seen in other years is fixes also last minute to insulate the coils from chassis, from other brackets. So we really recommend, well, first to have an insulation layer about your copper wires, also so that they don't touch each other and will create shorts or problems there. That's something that has been done in other years, is, for example, have a epoxy coating around it. So the coils are submerged in epoxy, and that is then cured and hardened so that not any copper is exposed to the outside. Something else is also that the coils must be mechanically secured so that they don't fly around. So you could do this either with the epoxy itself and then attach that epoxy, or just have a non-conductive bracket in some way securing those coils. And lastly, I would like to talk about the integration with propulsion. This is mainly, I focused on this last year, for example, for my design. Just wanted to give you a little bit of an idea of how I thought about, well, your integration with safety wheels and propulsion in that sense. So in this graph, you can see that there's a blue line, that's the force of the propulsion system does. And to that force, the force of levitation for different currents is added. So the middle one is the nominal current. So at 0 amperes, what the force is, and this will equate to the system weight. And basically, we had a range around that nominal air gap where your system is able to control the air gap in a proper way. So, for example, like I said, if your wheels compress too much and your system gets too close, your levitation system gets too close to the track, the magnet force will be greater than your system weight in the sense that you will not be able to lift off again. So that is something quite important to take into account. It can happen both ways. If you are too close and you cannot take off, or if you are too far away and then you cannot launch yourself. Yeah. So this was it from my side. Yeah, I would like to.
Okay, I don't see any questions yet. But just to make sure, again, from a jury point of view and from a scrutineering point of view, when you look at the pods at EHW in the next in Zurich, it's very nice to see a coil that has a connector that you just plug into a wire that plugs into your inverter, that plugs into your battery, and so on and so forth. So nothing that you have just two cables somehow put together with some isolation tape around it, or you need to isolate it afterwards because you forgot to do that before in the manufacturing process. So it's very nice to have all of that together. If you have had questions, just put them all in the chat. We'll wait a second for that as well. I like the levitation part of the Hyperloop seminar. I think that must be mine, right? Or is it someone else? I don't know. I think I've had one as well there.
Yeah.
Could we? I've seen. We could probably talk. We two can probably talk about magnetic levitation for hours. So we won't bore everyone without that. I like the HEMS as well. Maybe there's somebody. I've said that at EHW in Delft as well, when it was in Delft in the Netherlands. I want to see someone do a superconducting HEMS or a superconducting EMS with longer, higher forces, bigger air gap, something like that. Would be very, very great. Yeah, and I think I don't know if you've mentioned that. Yeah.
Oh, no, I was just gonna say then we'll have to set up rules for cryogenic cooling.
Yeah, that's true. I don't feel they are too dangerous because you can just pull off your hand, so don't stick your hand in it. But I feel like they could be kind of safe. Yeah, and you need to see where you get your liquid nitrogen and so on. And yeah, I think you mentioned all the linear induction, linear synchronous motors like that. But I just wanted to emphasize there is different versions of those motors that are very interesting as well. I think you premiered last year the linear flux switch terminal magnet motor. There's linear reluctance motors and so on and so forth. So there's a lot of different specified motors that you can really earn a lot of points with during EHW. So then we have a question from Cheyenne now. You can ask your question yourself if you like to.
Hi, can you hear me?
Yeah.
So it was regarding the ITT guideline. It was that in the RNR it says that it has 10 pages per subsystem, but in the ITT guideline it says that the system should not exceed 3 pages max. And is the system as in the traction or is the system as in the propulsion?
I am not very sure, to be honest. Do you know, Alejandro?
I'm wondering if it is a mistake here. It is totally feasible that we made a mistake, but the right answer is that basically the IDD, I believe it's around 60 pages max. So you have 50 pages, no, like 10 pages per subsystem. So here subsystem refers to any of the applications like traction, levitation, mechanical, sensing control, and electrical. Does that answer your question?
Yes, that is. Thank you.
You're welcome.
I think we put it differently in ITD guideline versus RNR, so we should change it.
Okay, is there a second question answered as well?
1 second for the follow-up for the previous question. The ITD guidelines state that the maximum number of pages for every subsystem is 3, whereas the RNR states it's 10, and subsystems are levitation, propulsion, mechanical, electrical, and sense and control. So it's like 3 pages per subsystem, right? So 15 pages. plus initial few pages for system overview, and then 3 pages at the end for the safety section, right?
Okay, so I think this query is more of the scope of a normal Hyperloop week mail query. So let's just ask the question there, and we will try to review it yourself and answer it as soon as possible, because
Cool,
it seems that there was a mistake.
Works, got it. Cool, we'll do that. Thank you.
Sorry?
We'll mail you that query and expect a response in the mailbox.
Okay, perfect. Then we'll answer as soon as possible. Thank you very much.
Cool, thank you.
Great. Also putting out some more questions on the rules and regulations. Yeah, those are always hard to write because you need to think of everything. But I think we can now move over to Alejandro and his presentation. And I think we'll just go over time here. So as long as you have questions, I think these two will answer them before we eventually need to go to bed all together in Europe, for example, at least. And let's see how everybody keeps up.
I mean, Mario's presentation was super good. I didn't have the opportunity to see it beforehand because I was actually preparing mine, so it was really enjoyable. I bet that after 80 minutes of seminar, everyone must be pretty tired. So luckily, mine is not as technical. I didn't put any references to anywhere because I'm a disaster with that. So I hope we can all just enjoy and learn something. I will be talking about batteries and software. So I will be just sharing my screen. So let's go with software and batteries, design and testing for a successful demonstration. So first of all, we will be looking at the index. So we will be seeing first electrical design for scale vehicles. Then we will be seeing testing batteries with high voltage. And then we will be seeing software design for embedded systems and embedded software testing methodologies. And actually the last two sections at the end were removed because we included in the embedded systems, as we thought there were not any specifics of control stations that were to any extra slides. So let's start electrical design for scale vehicles. Okay, so first of all, we have our electric system. Our electric system is mainly made of batteries, and we have to characterize those batteries. So here are the most important characteristics about them, which are the nominal voltage of the battery, the discharge curve, the capacity, the energy density versus the power density, which is some performance that we want to really look into. And then there's the internal resistance of the battery, which goes into how old is the battery or how many life cycles does it still have. So let's start with the basics in case someone missed. This graph is very important. This graph is like the main graph you may find in any datasheet about batteries. So first of all, the nominal voltage of a battery is its minimum voltage output during normal operation. So what does this mean? Here you have this graph, and this graph, what says is the amount of voltage that the battery is outputting on the y-axis versus the capacity it has, okay? So as the, unluckily for us, as the battery depletes, it outputs a different number of voltages. So like a different amount. It starts, for example, in LiPo batteries with 4.2 volts, and it depletes until 3.3. So first, the flatter, the better here, for the simple reason that if you have a battery that at 100% outputs a big amount of voltage, and then at 0% outputs a very little amount, then you have to do more dynamic conversion with the hardware and voltage converting and wherever. So first of all, we have the nominal voltage. So the nominal voltage is exactly this line here, and is the minimum amount of voltage you can use during normal operation. So normal operation is defined on the linear zone here. We have the nominal region, which is, as you can see, it's a straight line. And this zone is the one we want to use for two reasons mainly. The first being that the exponential zone on the left and the exponential zone at the right, as it says its name, it's not linear. So when you want to calculate how much percentage the battery has, it's very difficult because you cannot do a simple linear formula. And the second and most important reason is that it's not safe for the battery. It's not safe and it's not healthy. So if you work between a percentage around 20% or 30% and 70 or 80, the battery will just work much better. Okay, so let's leave this here. And why do you want to use the minimum value and not the maximum value? For the main reason is that this nominal voltage is your building block for your pack. So for example, one of the most popular cell type is lithium-ion cells, which have a nominal voltage of 3.7. And that means that any voltage under 3.7 goes into the exponential region, and it's not very nice to use. So if you want to build a battery of 9 volts, you will find that you can't, because you have one cell and it's 3.7, then you have 2 cells and it's 7.5, and then you go over 10. So that's something to take into consideration when building your battery. Next point, we have the discharge curve. Already explained it. It illustrates how its voltage changes over the duration of its discharge. And I said you want to keep it in the linear zone, so not much to say over here. Okay, so let's go now into the capacity. So the capacity is defined as the amount of electric charge it can deliver, and is typically measured in milliamperes hours. This is a very interesting unit, but basically what it means is that if a battery has 100 milliamperes per hour, for example, if you're working at operation conditions of 100 milliamperes, it will last an hour. And if you will work at double, if you work at 200, it will last half the time. It will last half an hour. So that's the standard way of measuring. Here you can see what I said, which is the usable capacity and the total capacity. So as you see, the usable capacity is smaller because there is this exponential zone you don't want to enter in for the safety of the battery. So next up, we have energy density versus power density. These are the main performance characteristics you will want to look into when comparing battery packs at the competition, and when comparing battery packs yourself at home, when you want to decide which are you going to buy for your vehicle or are you going to construct. So the energy density is the measure of how much energy a battery contains in proportion to its weight. And it's measured in watts per hour per kilogram. So, okay, let's go into power density and we'll see the metaphor afterwards. And power density on the other side is the measure of how quickly the energy can be delivered, and it's measured in watts per meter squared. So first of all, we have energy density. So here's a very simple metaphor. This is not very orthodox, but we'll assume that in this case that the amperes of the battery make up to the caffeine. So in this case, we have a coffee that is 12 ounces, and then we have 2.7 cans of Red Bull that is around 30 ounces. So as the coffee has the same amount of caffeine in less ounces, it has more energy density. So for battery capacity, it would be the same. If you have a battery that it's a liter in volume and it has more energy than a battery that has 5 liters in volume, that is more energy dense. And then for the power density, it is how much power it can output at some point. So why is this important? So for example, for your high voltage system, you will want to prioritize power density over energy density. Why? Because your demonstration at the competition won't last half an hour. It will last 30 seconds because your vehicle turns on, then it goes, and then bam, it breaks. So what you need is actually some batteries that can output the maximum current possible in the least time, so you can accelerate very quickly. While for your low voltage pack, you will want to have more energy density, or you will want to optimize that. Why? Because you will be working with your boards, with your control systems a lot more time. For example, on the scrutineering, you don't want the jury to come at the scrutineering and say, okay, my vehicle has 3 minutes of useful lifetime. So then they start doing the scrutiny and, we need to charge it. And then you charge it again. So you want at least a reasonable amount of time. Let's say half an hour, 40 minutes is something that starts on the reasonable. And here we have a very cool graph of energy density in batteries. So as you see, the main competitive type, when we are talking about energy density, it's Li-ion and LiPo, which is lithium ion and lithium polymer. We will see them later in this presentation. But basically you have on the y-axis gravimetric, which is very important because we are measuring energy density based on weight, which is very important to make a vehicle as light as possible. But then on the x-axis, we have the volumetric, which is I think, something that you will care more about, because we are talking about the space of the vehicle, and you will want to make a vehicle as smaller as possible generally. There is no graph here on power density, but, very important point to simplify this presentation, lithium polymer have greater power density than lithium ion, generally. I mean, there could be some exceptions, I don't know, but I believe that's how it is. So, lastly, we have the internal resistance. So here we have this very good graph in which we have our generator of energy, which in this case is the battery, and then we have a resistance. We have a very big resistance, which is the one of our system, the one in our vehicle. So this resistance should absorb all the voltage that's outputting from the battery. But in reality, this is not true, because there is a very small percentage that is sucked, let's say, by the battery itself. So this is the internal resistance of the battery. Different batteries have different internal resistances, and they also grow different with the life cycle. So what happens when a battery gets really old and you charge it and discharge it a lot of times is that the internal resistance increases a lot, which causes reduced efficiency. And eventually it's not only an efficiency problem, but it's also a temperature problem, because if the resistance is higher, it starts consuming more current, the battery itself, and eventually it heats up, so it's not useful. Okay, and now let's see some battery types. I'll go pretty quick on this since I don't want to take much time. With lead acid, this is your car battery. So it's common, cheap, reliable, and heavy. It's used in cars. And the problem is that it suffers from lower energy density. So it's not a good candidate for Hyperloop vehicles. Then we have lithium ion, which have very, very high energy density. They are lightweight, but they are pretty expensive, and they are used in modern electric vehicles. So yes, you could deduct that they are essentially a very good candidate for using in vehicles. And then we have lithium polymer, which have also very high energy density, although a bit less, I believe, than lithium ion, and they are very lightweight. And then being very lightweight causes them to have greater power density. Regarding to weight, they can output more power per kilogram. And very important, they are sensitive to mishandling. And then we have lithium iron phosphate, which, although not used at the competition, I believe they are a good option. They have been used recently by some companies. They are safer and longer lasting than most lithium, but they are less energy dense. So of course, if you don't have like a lot of spare space in your vehicle, you cannot use them, because you will want to optimize as much space as possible. And there's something I want to point here, and that is why should I care about the internal resistance of the battery? Because it's like, okay, but I'm just going to use my vehicle for a year. I'm just going to use this system for very few time. But I think that in this context of this competition, it's even more important, because imagine you mistreat your battery and you use it 0 to 100% all the time, which is also very risky. But let's say that best case scenario, the battery doesn't turn into fire and you just have a very, very used battery. And then the next year, your college or your public organization comes and says, okay, what happened to this battery? And you say, oh yeah, well, I use it very badly, so now you have to spend 1,000 euros again to buy a new pack. So we don't want that to happen, so always try to keep batteries in the 30 to 70 range, which is the most safe one. And here's the conclusion. If someone missed it, which battery type should I use? So we want to use lithium polymer batteries for optimal power density, and we want to use lithium ion batteries for optimal energy density. Okay, and then some design concerns, very important. It's like a rule of thumb, which is to leave a safety factor of 2 for the rated current of the system, and always leave a safety factor of 3 for the rated capacity of the system. So what this means is that if your total system, if your motor and your guiding system needs, let's say, 200 amperes, your system should be able to output 400 of continuous current, because batteries have 2 rated maximum currents. They have the continuous and they have the boosted current or boost current. So basically the continuous current is the one that they can continuously output in time as long as they are alive. So if the battery says 300 amperes, you can output 300 amperes from the battery all the time until it gets 0%. But then they have another current, which is the boost current. And for example, a battery with 300 amperes of continuous may have 500, may have 200 more amperes for boost current. And this is a current that the designer of the battery or the manufacturer says, okay, you can use it for 3 seconds or 2 seconds or 10 seconds. It's normally specified in the datasheet. And it should only be used in exceptional cases. Let's say if you do electromagnetic, well, no, not really, but only to be used in very, very specific cases. And then for the safety factor of 3 for the rated capacity, I think this is pretty obvious. If your system needs a capacity of 10 for a high voltage demonstration, don't have batteries with a capacity of 10, because then when you turn on your vehicle, the batteries will have depleted a bit, and then you cannot do the demonstration. And also when you're doing testing at home, you will want to do various runs in a single evening. So if a single run consumes 500 amperes per hour, and your system has 2,500 amperes, then you can do 5 runs. And that's pretty good, because you can do a lot more testing, you can do things a lot more quicker, and you do not need to extract batteries, which is also very risky, and it's not very fancy to do. Okay, so now let's go for the study case with the Swiss Loop high voltage battery, which is probably the maximum high voltage battery you would want to make. I don't see any reason to make a battery that has more consumption than this one. So as you see here, the design is pretty clear. You need as much power efficiency as you can. So you grab as many LiPo batteries as you can, you put them in series, and you don't worry about the capacity. Well, you're worrying a bit because LiPo batteries are also pretty good, but you're not aiming for that. As you see, there's not a single pack in parallel. There are 24 packs in series. And yeah, there's no more to say about this. It just gets the best ratio of power to weight. And then we have the EHW low voltage battery proposed in the standard proposal, which in this case, which kind of changes would you want to make from a high voltage system to a low voltage system? Well, as said, you will want to switch from lithium polymer probably to lithium ion, because now you are not optimizing power density, but you are optimizing energy density. So by making this slight change, you obtain a little better energy density. And then you will probably want to put some cells in parallel, because this way you obtain more use time, and then you can do more testing without having to recharge them one and again and again and again. So in this case, we wanted to build a 24 volts battery. So we have 7 Li-ion cells in series and 2 in parallel. So basically, when we put cells in parallel, we increase its capacity, but the voltage stays the same. And when we put them in series, the voltage is summed between the batteries. So 3.7 or 3.6 times 7 gives 25.2, and there are the maths. Not much to say about it. And are there any questions up to this point?
I don't see any yet in the chat, but again, I guess we'll give everybody a little bit of a time to go. I think in the last EHW awards, when putting something in a vacuum chamber to test, do the teams have to provide the power through low voltage battery for the whole test run? And remember that it could take longer than they might anticipate. Or if there's a vacuum chamber, can you also use a power cord or something? Also, when you're doing your own testing at home, what should be the consideration there for the teams?
Okay, I don't know if I understood the questions, but if the question is that if team can use the batteries in a vacuum test, I believe that a low voltage battery should be able to withstand, as said, at least half an hour. And I don't see why we should make a vacuum test longer than half an hour. Maybe I'm missing something. And for the vacuum test, we don't enforce teams in any way to do vacuum technology yet. But on the other side, if they want to do vacuum, we expect them to have tested them. It's not like, oh yeah, our system seems to be doing well, let's put it in vacuum and see what happens. Because if the system has not been simulated in vacuum, well, they may explode. So was that the question?
Yeah, yes, something like that. And then if you are testing in vacuum, you can also plug in a power supply, right? That you run into your vacuum chamber. You don't need to use your whole battery. So can you, do you need to use your batteries for the vacuum test? And they need to run for half an hour, 3/4 of an hour, how long your test goes.
Okay, yes, I think I understand now the question. So if you can, and if we have the possibility, in vacuum, it's always preferred to not use batteries for the purpose of the vacuum test, which will be just to test the control electronics, right? But as an advice for teams, let's not assume that you will have that possibility. Design your batteries to be self-sufficient.
Okay, and to last long enough for the whole duration of the whole test. Okay, which might be a little bit longer than you anticipate. And if your pot runs out as soon as you reach the minimal pressure, that would be very, very bad.
Exactly.
And,
Okay, so shall we continue, Lucas?
Yes, I think there's no questions on more and more. Mario, do you have an addition?
Now, I just wanted to add that it is something that maybe you should take into account if you want to do the vacuum test, because it already happened a couple of years ago, Delft, for example, that we ran out out of batteries basically. So take it in.
Just before the end pressure was reached, and you couldn't do the demonstrations anymore that you wanted to, or maybe the battery is too low in voltage, then that would be very, very bad. Okay. Yeah, I think we can go on with the presentation then.
Okay, so a nice conclusion. Put cells in parallel to have more capacity. Okay, so now testing batteries with high voltage. So first of all, we could look into what to do if there is an accident, what to do if something turns into fire, but the best thing is that nothing turns into fire. So how do we avoid accidents before they happen? There are a couple of things we can do to avoid any accidents, but I'd say that the most important one is actually to sleep. And this is something that we have to be conscious that 99% of accidents probably are caused by human errors, and human errors are avoidable. And if you're a programmer, if you're a CAD designer, you can have a day when you say, okay, I'm feeling like I have godlike skills. I'm going to work for 16 hours straight. And then worst case scenario, you just turn to be very unproductive. But when you're working with batteries, there's a risk. There's a risk of injuring yourself. There's a risk of injuring others. And there's a risk to injuring the image of the competition. So some common sense guideline, restrict battery testing to 9 to 5. Do not test batteries 1 a.m. in the morning. And do not test batteries if you don't feel like you're rested. You can postpone the test if feasible. We will try to help as much as we can from the competition side on that. So also get a spacious workspace. That's the second most important thing, because when you work in a space that it's not spacious enough, it's a lot more easy for accidents to happen, because when you're on a table where other people are working and there are screws on that table, maybe someone drops a book and then the screw jumps and that screw falls in a board and that board short circuits and then your battery goes into fire. So if you can go into a non-closed place, go into an open table where if there is a fire, the fumes of the battery will be able to go freely and you're not in an enclosed room, and that the table is just for yourself, and that you have enough space to separate the boards from the battery, yourself on the boards, yourself from the battery. The fire extinguisher, it's in a place where it doesn't disturb you, but you can access it quickly. So yes, I mean, these are things that we may say, yeah, it's very common sense, but we know people get tired and mistakes happen. And then other very important things, define clear battery responsibles. These are people that throughout the year should be the only people meant to manipulate batteries. They will have the responsibility of educating themselves and being educated on how to manipulate those batteries. And while being protagonists of the tests, of course, they may help, but if some engineer needs help with batteries, they have to be there to help, and they have to be the same people throughout the year so they can get as much kind of confidence as possible. So following that point, provide as much training and education as you can. There's never enough. As the team leads of your teams, try to read, ask any doubts, watch YouTube videos, and try to get informed as much as possible on batteries. And this is something that I cannot stress enough, and it's always use the appropriate number for the procedure. And in most cases, this will be 3. It will be one person who's just holding the fire extinguisher and maybe saying the procedure out loud. It will be someone who is directly manipulating the batteries, and it will be someone who is in the control station. And any more people than that, if there is extra people, probably it's just extra pressure. And under no circumstance, we want, when you're testing at home and you're going to do a battery test for the first time, the whole team looking at the side, because that's something very tempting. Everyone wants to see progress, but it's just pressure for those that are doing the test. So as much as possible, try to delay that moment where everyone is just seeing the procedure, where everyone is just looking, because if an accident happens, it's a lot more sketchy than if it's happening in an isolated 3-people environment. Once everything is validated, once you can even put the aerosol, then you can do kind of a public demonstration inside your team, but try to delay that as much because it's very important for safety. And then, of course, define all procedures beforehand and do progressive testing as early as you can. So if your system, if you want to test the BMS, if you want to test that it works, probably you don't need the 300 volts that your system requires. Probably with 50 volts, your BMS starts to work. So test a couple months with 50 volts, gets used to that. And if an accident happens, which is more probable because it's the first 2 months, you won't die because it's just 50 volts and it will be a lot safer. And it's also a nice way to kind of get an education on high voltage without actually fully risking your life. So yes, start with 50. When it works, add another pack. Now it's 75, now 100. Do not go all the way like, okay, it works with 50. We want to finish this deadline for this week. Let's just put 300 volts and see if it works, because maybe it doesn't. So now necessary materials for high voltage procedure. First thing, personal protective equipment, PPE. So use high voltage rated insulating gloves. These are your typical yellow gloves. So just as a clarification here, the freedom of your hands is also important for safety. So if you're working with 24 volts, there's no need for high voltage gloves. You can use more comfortable ones, okay? So let's try to find the balance here. Always use safety glasses, even if there are 0 volts, because the same, maybe a board gets heat up and then some capacitor just flies away and hits you in the eye and hurts you. So let's try to avoid that. And also use insulated work boots, which I believe do not need to be these big yellow boots, but can be some mountain-like boots, which are a lot more comfortable. So look into that. Also use a Class D fire extinguisher. There are a lot of fire extinguishers, but I believe that Class D one is the one that works for all, except grease and oil. So with this one, which is kind of the one with dry, it's the dry fire extinguisher, and it's the one that works for electric fires. Do not use the one that you find somewhere. Like, make sure it has the appropriate certificate and that it's up to date. And then, of course, use multimeters, voltage tenters, and whatever. And always have an emergency shutdown button. So it may be an MID, it may be an emergency button, it may be some command on your control station, but always have it prepared. Let not someone have to write, okay, let's stop the pod to stop the pod. And then what happens if we fail all of that? What happens if an electrical fire happens? So the consensus here, as I said, there are 3 responsibles. For me, responsible 1 is the one manipulating the batteries, is the one that is near everything, and the responsible 2 is the one with the fire extinguisher. So responsible 2, as soon as it happens, will press the fire extinguisher. Almost at the same time, the other one will press the MID, whatever happens first. But let's just do that instantaneously. And then once the situation is secured, dismount the setup pretty quickly for damage control and call the emergency services if necessary. And then enclose damaged batteries in non-flammable enclosure. So, okay, how do we know if a battery is damaged? Truth is that it is very complex. And companies which have a lot of money, what they do is, if there is a fire, they just throw away all the batteries. And that is the most safe thing to do. And if you can do that, just do that. But we know that batteries are expensive. So if you cannot, please, please, please do a thorough examination of every battery. if you have video recording, see which batteries got caught in fire. And if any battery has the minimum amount of physical evidence that there was a fire, just throw it away. And throw it away at a certified battery recycling center. Do not throw it away on a hole in the ground, because that's not a good thing to do. And finally, something very important, charging batteries is something that's very overlooked. That is something that can pose a lot of risks, because same as if a battery gets discharged and you keep discharging, it turns into fire. If you charge it above the 4.2 volts of maximum voltage for Leon, it can also get very, very damaged. So use a certified charger for day-to-day charging. Do not cut costs on this. Just search on the internet a very good charger. Some teams try to build their own charger proposals for the competition. It's something very, very ambitious. And if you manage to have it done, you will have it done by the end of June. So in any case, you will need a certified charger. Just go on the internet, find someone, and charge your batteries with that. End of the story. And unless necessary, keep the state of charge in the linear zone. The state of charge is the percentage of the battery. So keep it in the linear, which is for Leon and Lipo between 30% and 70% of state of charge, or if you're measuring voltage, it's 3.7 volts and 4.2. And never, never, never charge batteries without supervision. Every commercial charger that you might buy automatically stops when the battery is charged. But still, always be looking at the batteries. You never know what can happen, and it's your responsibility if you put them to charge. So always be supervised, please. Any questions?
I think there's one question from Alexei. He asks, how do you prioritize the aspects of safety and which one is most important?
How do you prioritize aspects of safety? Well, I think it's a very general question. Ideally, you prioritize safety in itself. You want to cover everything. And if you cannot cover every critical aspect, do not do the procedure. And maybe some alternative answer when an accident happens and it gets totally out of control, out of the scope of what we seen in these slides, it's always the same procedure. Protect yourself, make others know that there has been an accident, like call emergency services or whatever, and then go help the person. Like, okay, go help the person as quick as possible. But if someone is having kind of an electrical attack, do not go immediately and grab him, because you will have an electrical attack too. So does that answer the question?
Yes, thank you very much.
Maybe I can add something as well. So I would recommend, for example, you could go through what a normal operation of your battery would be. So I don't know, charging it, then discharging it, or just the normal operation of the battery, and you can go into what could potentially go wrong at each of the stages, and just look at the risks of that, and basically set up like a scale of risks of what is acceptable and what is not acceptable. And then you have to implement a mitigation strategy or a change in your design, so that the ones that are not, those risks that are not acceptable, move into an acceptable level. So yeah, I hope that
yeah, thank you very much.
I think that's part of some safety documentations as well, with the safety analysis that you do, mitigation techniques, how likely it is, and so on and so forth. So there's stuff that you do in the documentation.
Yes, I think that risk mitigation, we could have another 2-hour talk about that probably. So let's go to the next point if there are no more questions, right? So it's software design for embedded systems. So let's please first define what is an embedded system. So I really like this description from Wikipedia. An embedded system is a combination of a computer processor, a computer memory, and an input-output peripheral that has a dedicated function within a larger mechanical electronic system. I really like the part at the end where it says that has a dedicated function within a larger system, because it denotes that it is indeed made to serve the vehicle itself. That it's not independent in itself, but it makes other things work. It makes the mechanical system work. It makes the brakes brake. It makes the motor accelerate. So it always has that complementarity. So how to design embedded software? So the first step is to actually design something. And with this, I mean that when we want to design some mechanical system, it's pretty obvious that we have to go into CAD and we have to start making some sketches, and then we have to do some simulations, and then we have to do some validation and wherever. But sometimes when we develop code, we find that we think that we start coding and suddenly the code starts building on itself, and then you have the complete system for the vehicle. And normally it's quite the opposite. You start coding, then you realize that your code doesn't meet the requirements, and then you have to build up that badly written code. So before you start to actually write the first line, make sure you have a minimum amount of work done. So this would be, please, first use UML diagrams. So to be fair, I don't like UML diagrams. I think they are pretty boring. I think you have to take a lot of time to make them. But as much as I hate to admit it, they are very useful because they are the standard way of communicating software or of communicating requirements. And it will be a documentation in itself for the next years. And imagine you had a sponsor from a very good software company. Let's say you get a sponsor from Google, and then Google says, okay, we can send this engineer, this tech lead, to help you with your system and to advise you, because that's a very common form of sponsoring these days for teams. Teams get people inside the companies to actually give them advice, and that's fine. If your code is just a bunch of hand-drawn sketches, probably that person that takes the day to come and help you will spend the whole morning trying to understand those sketches. And on the other side, if you have the UML diagrams, that's universal language. So you can send it to him, he can see it beforehand, and you will get a lot more out of that collaboration. And as well as it works with some company, it works with your partners inside your firmware system. So always, please try to make UML diagrams. Also use some kind of version control. So let's try to keep it a bit out of brand here, but there is the main leading version control software, which is Git, and it works pretty well. So reasons why you would want to use version control is history tracking, which is a form of documentation in itself. You want to see, okay, when did we actually implement this feature? Who implemented it? What did we implement? So that kind of history is what you want to track always. There's also branching and merging. So branching is when you have a version of your code and then you create a parallel timeline, let's say, and then you work adding an experimental feature in that timeline without modifying the stable version. So if someone needs the code for tomorrow for the vehicle, they will not find your unfinished experimental feature. They will find the stable version. So that's what I've done. And merging is the opposite process. When you grab your parallel timeline and you merge it. Once, of course, it's been reviewed 1,000 times and you have tested that it works. So another reason to use version control is to do a code review, because before merging a set, your other colleagues can review that code. And I think it's a very beneficial process, because it doesn't only help to spot errors, but it also helps to get everyone to know the code, because in an environment as agile as a Hyperloop team, someone might not be able to come to work one day, and they might need their system, and you will have to use to make the work they didn't do. So you will have to know their code. So code review is a nice way to overcome that barrier. And also traceability, which basically means that if someone, to say gently, uploads some code that doesn't work, we know who was and what was, with the purpose of just fixing it, of course. So here's an example of a pull request that you might do, which was done by me last year. So a pull request should include a brief description of what you are trying to merge into the main branch, what changes you are doing to the code. And it's always nice when you just add a snippet of, okay, how do we use this? And this is not a standard documentation, but probably there are a lot of things that you won't have time to do standard documentation because the year is very short. So at least you have this safe upload to the internet that if someone comes next year, okay, there is not a standard documentation, and there is this obscure pull by this guy, and you can use it. And sometimes it may be enough. So another thing is to use Gantt. So that's the last thing I would say to make software requirement, which is pretty straightforward. As you see on the y-axis, you have a bunch of tasks of projects, and then on the x-axis, you have the timeline for the dates, and then you can assign responsibles. So just write all the tasks you have to do and see that no one has any overlapping tasks, because if someone has any overlapping tasks, it probably means that you won't finish on time. Okay, and then the final and probably most important part, how to set up requirements for the code itself. So when you set up requirements, you say, okay, we need a code that can read from those sensors at this rate and says this kind of message to the control station. And with that, what you obtain is that you can write code that does what is requested, and you do not need to write code that does everything. So this is pretty clear when, for example, when you're building communication. It might be very fancy to build an omnipotent communication system that can do everything, but most of the time it will be a daunting task. And if you're able to do it, then it's fine. But it's a lot easier if you say, okay, what size of packet are we going to use? Because we can use a 32-bit size of packet, and then your packets can be fixed size. And if your data is smaller, just add zeros at the end or wherever. And it makes a lot of things easier. And also communicate with other subsystems, because you can have this problem like, oh, do we need to build our ADCs, which read voltages at this speed? I don't know, but that's not a question for you. Just ask the levitation guys what rate of information do they need for the control, and just ask the same to the propulsion guys. And that should answer your question. Okay, so now we can actually start to code after setting all these requirements. So some bad coding practices you want to avoid when coding, and that are seen in previous editions, are to hard code a lot of values, to not do any error handling, to ignore real-time constraints, and to do things later on which are never done. So most important and most technical of these probably is the real-time constraint. You have to take into account that you're building a real-time system. And this means that your code will not be sequential, because an event A might happen after event B, or it might happen earlier. You don't know, because you don't know when you want to break. You don't know when the sensor is going to read an out of bounds value. So you have to build accordingly. And if you want more information, you should really look into real-time operating systems, how they work, and probably implement one of the existent into your firmware system, or build your own. And if your system is simple enough, you can do a simplification of it. Okay, so this is some example. This is some code that probably will be in everyone's system that levitates, which is to calculate the PID, because as far as we've seen, all vehicles right now levitate with PIDs. So we have here some hard-coded numbers, which are not very clear, and you can replace them with the P, the I, and the D, and probably the next person that comes gets it a lot easier to read it. And with this, we have some good coding practices, which is the opposite of pure naming, is doing meaningful naming. Then you should also write modular code. And with modular code, it's code that can be grabbed from one place and used in another. And this is very important, because in the end of the day, most boards do the same. They just read sensors, they just send values to the control station. And you do not want every programmer to write that in a different way, because then everyone does the same work, and probably it has different mistakes. So that's double trouble. So if one person writes its module and then everyone uses other people's modules, it's a lot easier to work on. And then also very important, try to write why comments and not what comments. So if a comment explains what something is, then you can probably just replace the name of that thing into a more clear name. We should only write comments about why am I implementing this change. So here we have some clear example. You have a variable t, which is time. You might do time in seconds, because that makes it a lot more explicit. And then let's not be redundant either. So we have a class that it's ADC sensor, and then it has a function. You don't need to call that function get ADC sensor voltage value. It can just be called get value, because you know it's from the sensor itself. So was there any question up until here, Lucas?
I don't see any.
Okay,
It should be fine.
perfect. Let's continue then. So just to finish up, and this be pretty quick, how to develop testing. So the most important thing when developing code for embedded systems is that when the boards arrive, code must be finished. And this is very important because once the boards arrive, you will have very, very little time until the competition. And if you have some kind of failure, for example, this code is not working, then you're wasting time because that time could be used to solve the errors related to the hardware board itself that just arrived. So try to make a plan where ideally all code is finished by the time your respective boards start to arrive. And then only need to write code for fixing the board specific things themselves. So first thing you want to do with the boards is manual testing. You can create all kinds of testing methodologies. You can create and use all kinds of automated things, but at the end of the day, you will spend most of your time doing manual testing. And this means grabbing your board, grabbing your oscilloscope, and testing that things manually work. And you have to do those things well because it's where you will spend the majority of your time. So before starting and spending a lot of hours doing things, write what you're going to do in a test procedure and then document it. Because if not, someone will probably come next week and do the same. And get evaluation boards. This is something that I think all teams do, but if you're not doing it, you create your custom boards, hardware boards, and they use a microcontroller. Probably there's an evaluation board for that microcontroller, and that is a board that uses that same microcontroller, but has all the hardware around it validated. So if you upload some code to a board and it doesn't work, then you have this discussion. Okay, is it my code that it doesn't work, or is it the board? Okay, that's pretty easy to solve because you go into the evaluation board and you upload it there. And if it works on the evaluation board, it's the hardware. And if it doesn't, then it's your code. So that saves a lot of time. And then after all of that is done and validated, you can implement unit testing, which is that everything that doesn't require physical testing can be tested automatically. So this means that you grab some functions. For example, you want to test that some arithmetic is done correctly. So you create a function that grabs your actual code and says, okay, I'm going to test this. And if it doesn't return 4, it's a mistake. This is very difficult to do in firmware because actually most things do require physical components. You always need some kind of sensor, you always need some kind of battery. So what we can do is that we can mock up these things. So by mocking up things, we mean that we can just kind of build a toy version of that thing. So for a sensor, it's pretty straightforward. If you want to test your code, you do not need a fully functional sensor. What you can use is just a function that returns a random value, and that random value will be your sensor. And with that, you can test your code. You can test if the value goes out of bounds. You can test if the value reads at the frequency that is intended. And then after all those things, you can do integration testing. So integration testing is very important because when put together, things break always. So something might work. You have a module A that works. For example, your control station works and your sensor reading works. But suddenly, when you put them together, they don't work because they have problems that only appear when they are together. So before putting things as late as possible into the competition, try to do it very early. Try to be good on time. Try to have anything finished by March. And then you start integrating things. And also very important, make sure that the individual modules are properly validated because integration testing is completely useless if when things doesn't work, you start to doubt like, okay, maybe this didn't work that well. No, things should work very well individually and then you tie them together. And for this, it is not necessary to go into every specific values. Just use the real environment that you will have at the demonstration day. And if it works with those values, it will work probably. So any questions?
Again, I don't see any. I just had one thought that came into my mind. You said Gantt charts are important. Yes, Gantt charts are important also for mechanical engineering. Because if you have a wheel or something or a gear that needs to be heat treated and you don't take that into account at the beginning, and that gives you 6 weeks on top at the end, that's like game over there. I like your prototyping ideas as well. Also in mechanical, just to get that across again, you can do like foam, styrofoam models where you can look where sensors are located, look where cables are running, see if cables are running over coils, over motors or something that might put a 50 volts on your CAN bus that normally has 5 volts and you can't read anything anymore. So it's really nice to like prototype also in mechanical that way. Just an idea that I still had, but I think that's all.
Yeah, completely agree. So if anyone has any questions, this was the end. Thank you for your attention. Here you have our contact details. You have our name on LinkedIn and our mail. At least for me, I don't know, Mario, I'm not famous enough yet, so I don't receive many mails. So you can just directly mail me to my personal. And thank you very much, everyone, for your attention. That was it for me.
Okay, great. Thanks everyone for attending. Maybe there's one more question coming up. In the meantime, just as a scrutineer from the last years, there's nothing more on the electrical side that scrutineers hate, that are kind of like loose cables or jumper wires that are connected on boards, healthier tape, and that should last your pods run. So make sure you have everything wired and properly connected beforehand, and think about safety before. Make good designs and then take them to the competition week, because everything you figure out there, you could have figured out before.
Yeah, and think about where your wires are going to go as well. I know when you're designing, you're like, yeah, these wires will just go through here. But once you're getting the physical prototype, what 5 millimeters seems enough in your CAD design, it will not be enough in your prototype. There's turning radius in your wires as well. So yeah, good to take into account.
Yeah. So I guess we can end the EHW part here, and everybody who wants to talk about Hyperloop still can stay in. I'll end the recording here, and I would just say see you all again then next week, or this week on Wednesday, because there's a seminar with the thermal management component. So see you all there, and then let's discuss Hyperloop in case anybody is still interested.